Okay, this is another bomb calorimeter heat capacity, example number 2. When exactly 1 mole of anthracene, C14H10, is burned in a bomb calorimeter, the energy change is equal to minus 7,053.5 kilojoules. Our first job is to write the combustion reaction. So we will take C14H10 as a solid, and we would like to form CO2 as a gas and H2O as a liquid. So we will need 14 of these and 5 of these, and our amount of oxygen gas, when we tally it up, looks like a very odd number. It is 28 plus 5, so that is 33 halves of a mole of oxygen, which is also 16.5. Okay, that's question A. Next question. Determine delta H per mole for the combustion of anthracene at 298 K. Okay, you may recall that energy change is equal to enthalpy plus work. We are given the energy change for 1 mole, that is minus 7,053.5. So, if we could just figure out work, we could solve for delta H. Work, you may remember, is equal to minus delta NG RT. So, delta NG for our reaction has to be equal to 14 minus 16.5. So that would be a minus 2.5 moles of gas per 1 mole of anthracene times R, and I will keep it in kilojoules since that makes my life easier, per mole gas Kelvin, and we're working at 298. So, typing that value in, a minus gives me a plus, right, because this is a minus 2.5, so eventually my value comes out to be a positive 6.1939 kilojoules per mole of reaction. So back here, plus 6.1939 kilojoules per mole of reaction, and I will just do the math, and that turns out to be negative 7,059.7 kilojoules per mole is equal to delta H. So, there we go, we just corrected it for work. Last question. When 1.7148 grams of anthracene was burned in a bomb calorimeter, the temperature rose from 20.45 degrees Celsius to 29.67 degrees Celsius. What is the heat capacity of this calorimeter? Okay, you may remember that the heat capacity change in the calorimeter is equal to the heat capacity times the change in temperature. It's easy for us to find the change in temperature. That is going to be equal to 29.67 minus 20.45. What we need to find is the heat exchange of the calorimeter. Now, the heat change of the calorimeter is going to be the opposite of the heat change of the reaction that occurs in that calorimeter, and we can figure that out by our delta E. We have 1.7148 grams of anthracene, which is C14H10. So, I need to get my molar mass of my anthracene, so that would be 178.22 grams of anthracene per 1 mole of anthracene. And this is a bomb calorimeter, so I don't want to take my delta H value. I actually want to go back and take my delta E value, because we want heat change under constant volume. And that would be minus 7,053.5 kilojoules per 1 mole of anthracene. So I will multiply this out, and I will determine that this is minus 67.867 kilojoules for this particular reaction in which I used 1.7 grams of material. That means Q calorimeter is going to be equal to a plus 67.867 kilojoules. So all that's left now to solve for my heat capacity is to take 67.867 and divide it by 9.22. I determined that the heat capacity of my bomb calorimeter is 7.361 kilojoules per degree Celsius. And that is my answer for example 2, and I guess technically it's only good to 3 sig figs since my temperature difference was only good to 3 sig figs. So that one's all done.